Cool. Yay, excellent. All right. Well, this is our last class for CSE 222. So, congratulations. This is almost certainly the most difficult course in the entire CSE sequence. Um, and a really good job coming through this. I think everybody has learned a bunch of important concepts, recursion, and data structures, and people seem a lot more comfortable with dynamic memory and pointers and mallocs and that kind of stuff. And there's still going to be fuzziness around that. That's okay, but from what I've seen, people have just really sort of come super far in figuring out these fundamental concepts. So I think everybody's in good shape in here. Looking forward to CSE 223. That's a really fun course. We work on much bigger projects, but we work on projects that kind of do more interesting things. We'll be making some games. We'll be doing some networking, some multi-threading, things like that. So that's a really fun class, and we leave C and move into Java, which is a object-oriented language. It's basically the language that a lot of Android development is done in. It's a modern language in a lot of senses, and it's a very different feeling usually from writing in C. C, you're kind of down in the nuts and bolts, putting together small pieces and putting those together into bigger and so on. With Java, we're at a much higher level, and we're starting with these very large chunks of code with all sorts of capability and putting those together to do even larger things. So yeah, we'll definitely do some networking. We'll do some GUI development. I'll probably have a game development, homework assignment, and it's just lots of good stuff. So definitely looking forward to that. And so let's yeah, online chess would be cool. Totally. Let's go through this study guide. But first, any questions that you want to talk about, either from the study guide or from anything else? Anything you want to go over first? Whoever made that is like genius. All right. Well, we started going through this yesterday, so let's just continue with this. Let's see. So we were talking about linked lists. So basic operations on a linked list. So how do you search a list? How do you print a list? How do you move down a list in general? So starting from the Sentinel node, you follow the pointers basically, and that's kind of a recurring theme in all of the kinds of things that we want to do with linked lists. Let me try to make this text a little bigger. All right. Inserting, right? Same thing. Move down the list, and when you get to the spot where you want to do an insert, then you go ahead and adjust the pointers. And the main thing that we get out of working with linked lists is this idea of manipulating memory, right? So trying to get comfortable with the idea of following a data structure and getting to, for us, for lists, it was usually something like previous and current. And then being able to do things like, new equals malloc. And setting a data value and so on. And then if we want to squeeze this new node in between, it's really just, new next equals current, previous next equals new, to do this kind of thing, right? And that's really the essence of the kind of action part of all the code you've been writing for trees and lists and stacks and queues, right? Is basically manipulating pointers like this. And so that's been a big goal of the course, is being able to write and understand that kind of code. Yeah, definitely. So so that really gets you through, all the basic list operations, inserting, deleting, and so on. Doubly linked list is just where you have, forward and backward pointers on each node. We didn't really do anything with those, but just be aware of what they are, so that we might have an extra node. Instead of next, we have another node, previous, that points in the other direction. And it's just a convenient way, if you're moving through a list looking for something, it lets you get back to the previous node without having to keep track of previous current and move those down the list. You should know something about order of complexity. We haven't gone into a lot of depth on that, but basically, how does the amount of work you have to do change as a problem changes? So this idea that, with a linked list, if you want to search for something, it's basically order n, because all you can do is just move from one number to the next until you find your thing or get to the end and don't find it. With a sorted array, it's log n, because you can keep cutting the list in half and play high-low. So those kinds of things, and this idea that we can insert into the middle of a linked list in fixed time. We don't have to move things around, whereas with an array, if you want to insert in the middle, you've got to move all the things below that insertion one spot down. That's back to an order n operation. All right, we talked about dot and arrow yesterday. So when you have a structure has a set of fields. Those are the pieces of the structure. If you actually have a structure, you can say dot field name to access a field. But if you have a pointer to a structure, you say arrow field name. And that says, see what this points to, and then, do a dot, give me that field name. And star and ampersand, so I don't think there's a lot of confusion about this anymore, but, star pointer equals the thing pointed to by this variable, which is the memory contents at the address given by a pointer. And then ampersand var equals the address of that variable. And they're sort of opposite instructions, right? Opposite concepts. So if I have a variable, I can find its address by putting an ampersand in front. If I have the address of something, I can find what's at that address by typing in a star in front of it. So they kind of, do the opposite things. And so if I did star ampersand var, technically that's the same thing as var. This says find me the address. This says find me what's at that address. Well, it's just going to be var. All right, pass by value and pass by reference. So, the main thing to remember is that in C, star star add var, oh, fancy. The simple truth is C always passes by value. So if I have, some function, so here's my main program, and I've got an integer I equals 10, and I say call my function I, and over here is my function. When I get inside my function, since I have an argument named I gets set equal to whatever value I passed, which in this case would be 10. But this I has nothing to do with this I. They're completely separate variables. And that means if I change I in here to 11, when I come back from my function, I is still 10. Right? Because this is a totally separate variable. And so if instead, I had called my function with an argument ha, and I say ha equals 11, it's easier to believe that's not going to affect this variable I. Right? Ha is a local variable. It's only meaningful inside my function. And when I call my func I, that's exactly the same thing as if I had said my func 10. And now it's completely believable. If I call my function with an argument of 10, and inside here I said ha to 11, we have no expectation that that's going to change the value of this variable I. Right? We didn't even mention I to my func, and my func has no access to this variable, right? So that's what pass by value is. When you call a function, this I is basically replaced with the value of the variable I. And that's all that C ever does. It's always pass by value. But we can pretend that we're passing by reference by using this notion of ampersands and stars. So suppose we actually want to modify the value of I up here. Now if we call my func 10, we can't change the value of 10. But we may want to call my func and have my function change the value of this to 11. And so if we want that to happen, here's what we can do. So here's main, here's my integer I, which I'll set to 10. And I'll do some stuff, and then I'll call my function. But I'll pass the address of I. And then in my function, I'll say I'm not getting an integer, I'm getting a pointer to an integer, which I'll call ha. And instead of setting ha equal to 11, I'll say star ha equals 11. Alright, now we have a very different situation. I'm going to pass the location in memory where this is stored, even though I belongs to the main program and is not directly accessible in here. If I say I equals, it doesn't refer to that. But I'm passing the location in memory where this is stored. Right? That location is one location for the whole program. And so if I use that location inside this different function, it still refers to that same variable I. Cool. So down here, ha is the address of I. Star ha says, what is stored at that address? Whatever it is, change it to 11. That changes this I to an 11. So this is one of these things where you know, after you've been messing around with pointers pretty intensely for 20 some weeks, even if you hear the same explanation you heard a year ago, it's going to probably resonate more. So yeah, after working with Malik and after working with some of the stuff and debugging and so on, it'll start to click. And that's totally the nature of learning, most things. It's like the more you work with it, the more your brain is prepared to understand. And you could hear, the exact same definition that you heard, earlier, and it can mean something much more after after some conditioning. So yeah, that's basically pointers. And at the risk of complicating it, right? This is still being passed by value, but what's the value being passed? It's the address of I, right? And if I change ha ha, that doesn't change the address of I, right? But if I change star ha ha, that changes the thing that I points to. All right, so we think of this as pass by reference. And it basically means we're passing a reference to I. So we're passing I by reference in this case. All right, malloc and free. So malloc is what we do when we want to get a location in memory that we can use. And so, here I was passing the address of I, but I could have done this differently. I could have said integer star I, and then in main I could have said star I equals 10, and then I could have called my function with a value of I. And that would work just as well, except this is going to segfault the way I've written this. Now when I say integer I equals 10, a few things happen. The compiler and loader get together and say, hey, we got to have an integer I somewhere. And they figure out where to store that, and then anytime that the program accesses I, it looks at that location. And it also stores a 10 at that location. When I say integer star I, all that says is I is a pointer. It can refer to somewhere in memory. But it hasn't been initialized. And so if I say, let's go to where I is pointing, where is it pointing? Probably 0, which is not a valid location. So I need to give I an address, and so that's typically where we would use malloc. And we would malloc the size of an integer because we want it to be big enough to store an integer. And anytime that you malloc, eventually you want to free. So you know all about memory leaks now. You're like super prepared for not getting memory leaks down the road too. So when you malloc, you have to eventually free, and valgrind is a nice tool to help you identify memory leaks. So that's the malloc free pair. Let's see, GDB. So I'm people are starting to use GDB more, which is good. You should know the basic highlights of debugging with GDB. So compiling, you have to put a G switch somewhere, and one way to do that is just right after GCC, just do a -G. But you can put it pretty much anywhere in the line, except between -O and an output file. Remember, whenever you say -O, that's got to be followed by the output file name. And this says, instead of making a.out, make this executable file. And you can't put anything in between here. Whatever comes after -O, that's the output file. So if you say -O-G, you get an output file named -G. So don't ever split these up. But the -G can go pretty much anywhere. And to run your program, GDB program name, and you can set breakpoints, so that's useful. And you can break at a function or at a line number. You can say list to look at your code. You can say start or run. You can say continue to tell it to continue running until it hits a breakpoint. You can say next which steps one instruction. You can say step, which steps one instruction, but also goes inside function calls. You can print a variable or an expression. You can say examine some location in memory. You can set a watch point on a variable, which will act like a break whenever that variable changes. I think those are the biggies. I think that gets you, enough to do most of what you want to do. And when you start or run, you can put arguments after that if you want command line arguments to your program. Unfortunately, we don't have GDB when we get into Java. There's a Java debugger, JDB, which honestly I have not had a lot of success with. I just need to learn some fundamental concepts, I think, with that. But we won't get much chance to use GDB in 223, but you definitely will at a university. All right, so that's GDB. Makefiles. So people are doing makefiles on their assignments, which is great. Not a whole lot to say about that. So, I mean, from what I'm seeing, everybody knows how to create a makefile, how to use it. So it's just a way to, systematically describe what has to get compiled, what has to get linked to build some target. Abstract data types, I think we talked about yesterday, but, basically the idea of what the user sees in working with a data structure versus how that data structure is actually implemented. So quintessential example is linked list for us, right? We had two totally different implementations of a linked list, but our main program basically did the same things, right? Call initialize, call insert, call search, and so on and so forth. Recursion. So you've been doing lots of recursion for trees in particular, and also for some of our sorts. Recursion, recursive algorithms programming, writing recursive code from recursive definitions. So make sure you're comfortable with this. Go back and look at the definition for the height of a tree, for example, as being, 1 plus the height of the largest subtree. Or telling if a tree is balanced by, making sure the heights are close and making sure the two subtrees are balanced. So those kinds of recursive definitions, when we describe something in terms of itself, taking that and turning it into code, right? And that's super powerful to be able to do that. So implementing recursive algorithms in code. And if you want, you can start thinking about other algorithms that could be written recursively. And so one example, is factorials. Right, we can think of n factorial as just, n times n minus 1 factorial. And we always need a base case, so this is 1 if n is less than or equal to 1. But we can think of other things. For example, the length of a string. So the length of a string is 0 if the first character is the null terminator. Otherwise, it's 1 plus the length of the string starting at character 1. And that's a little confusing to write in C. But if we have a way to say, well, let's take the string starting from the first character instead of, the 0th character, find the length of that, add 1 to it, that's the length of the original string. So you can start thinking about lots of algorithms as recursive, um, and that's pretty powerful too. All right, let's see. When we started learning Java in 223, you start from the beginning. Correct. Yes. So we don't assume any experience with Java. We don't assume any experience with object-oriented code. Nothing. So we start from just the bare beginning. Yeah. Definitely. All right. Let's see. Stacks, queues. We played with those. I think we did some ODPs on them. I think you had some quiz questions on them, um, and some coding. So main thing to remember: stack is a LIFO, queue is a FIFO, and concepts related to a stack, top of a stack, which is the part where the place on the stack where you're about to add something or remove something. Push is a way we add something to the stack. Pop is how we remove from the stack. We always pop the thing that we just pushed. With a FIFO, we have an add and a remove. And we always add or insert at the tail. And we always remove from the head. So instead of a top of stack, which is where both of these happen in a stack, we have two pointers. We have a pointer to where we're inserting and a pointer to where we're removing. Underflow when you try to pop from an empty stack. Overflow when you try to push into a full stack. And we can implement this with a linked list. You did that, and you can also implement it with an array where your stack pointer, it just tells you where in the array the top of the stack is. Queue, same thing, empty implementation with a circular array or a list. So we implemented these with lists, but we could also implement these with an array, and the array is circular. So here's your array, and let's say you're inserting at the tail. So the tail starts here, you insert something, the tail moves there, and it moves there, and so on. And maybe you remove at some point, right? And our tail moves over to the end. Well, if we want to insert one more thing, we don't move over here where we'd get, a seg fault. We wrap back around, and the tail moves back to the beginning. And so the effect is as if, this array was, a snake eating its tail. So that when we add to this thing, the next place that we add is back to here, and so on. Hashes. So we didn't do a lot of programming around hashes. We did some ODPs, but main thing to know, right? So the basic idea of a hash is a way to implement an associative array. So we can take a key and we can use that basically as an index and say, here's some data, store it somewhere based on this key. And if our key was an integer from 0 to 10, we could just use that key as an index into an array. But if our key is something like a name, we need a way to turn that into an integer, which is an index. That's what the hash function does. So basically we take a key, data pair, we have an array, which has a key and a data pair. And so if you want to store a key, we take the key, we run it through this hash function, and we get out an index. And it says, you know, the index is 2, so this is where we store the key, and this is where we store the corresponding data. That's the basic, you know, ideal behavior of a hash. Let's see, might have been useful for PA5. Yeah, I could see that. You could do that if you wanted to look up items, for example. That would be useful. Hashes are nice when you want to do something with, you know, parallel arrays, like, you know, storing items from your knapsack and stuff, but you want to be able to do things like search through those pretty quickly. Yeah, don't forget PA6. Alright, so basic operation, take your key, run it through a hash function to turn it into an integer, and that integer is an index where you should store the key and data pair. Okay, that's an ideal hash with no collisions involved. But the problem is multiple keys will hash to the same thing, and so we get into this issue of collisions. And if we had 2 or more keys that map to the same index, we can't store them all here because this is just one spot for a key, one spot for a data. So we have 2 approaches to dealing with this, and you should be familiar with both of these. The first is what we call probing. And probing simply means, okay, we tried to store our key right here, that spot was in use, let's rehash. So we use effectively a different hash function, and the way we do that is we have a probe number, or an attempt number, and the first time we try to hash our key, we set, you know, our attempt number equal to 0, we get some index. If that index is in use, increment this and rehash with a probe of 1. And that should give us some different location. And if that location is free, we use it. If not, rehash with a probe of 2. And keep trying different hashes until you find a spot where you can store it. So that's probing. The other approach to collision management is chaining. And with chaining, instead of actually storing the data here, we store a pointer to a linked list. And we would just store key data pairs in that list. So it's kind of like a hybrid between hashes and linked lists. We could just store everything in a linked list, but if you've got, you know, a million pieces of data, you might have to search through a million things in your linked list. But if you can have a hash table with, you know, say 1,000 entries in it, generally, you know, the longest your linked list would be for one particular key is 1,000. So you take your key, you hash it, you find a smaller linked list, and then you just search that linearly. So that's chaining. And those are 2 approaches to collision management. There's other approaches we could take too. And then when we implement this with arrays, we looked a little bit at deletion. And deletion gets funny because if we're using probing, right, when we search for a key, if we hash our key and we find something here that's not the key we want, it's some different key, we know we need to rehash with a different probe number. So if at some point this gets deleted, we need to remember that there used to be something here. So then when we look for this key and we hash and it brings us here and we don't find our key, we can say, oh, but we might have had a collision when we tried to store there. So we just have a deleted flag. So we end up with all this extra stuff. There's a valid field, there's a deleted field, and so on and so forth. Alright, so trees. This has been the bulk of the second half of the course. So binary search trees, right? Basic characteristic. Things to the left of the root are smaller, things to the right are bigger. And let's see. So depth of a node is the number of hops from the root to the node. So the root has a depth of 0, right? So it's not the number of nodes that you count, it's the number of hops that you make from the root. And then the height of the tree is the depth of the deepest node. And so if you only have a root, the height will be 0 because the depth of the root is 0. And then by definition, if the tree is empty, we call the height minus 1. And we have recursive definitions for height, 1 plus the height of the tallest subtree. And we have a recursive definition for balance. And you've coded these. Traversal, so we have three depth first traversals that we talked about. So in order, where the node's in the middle, pre-order, where the node is first, and post-order, where the node is last. Those are all depth first. They travel deeper before they move across. An alternative is breadth first, where we move across each level before we go down to the next one. And just like we can implement depth first using a stack, we implement breadth first using a queue. And then searching and inserting, we basically generally do that using recursion. So how do you search for something in a tree? Is it the root? No. Is it smaller than the root? Yeah, okay, check the left subtree. How do you do that? Use the search function. So that's the essence of recursion. And inserting, is it smaller than the root? No, it's bigger than the root. Okay, insert it into the right subtree. And we do that using the insert function. All right, and deletion, we did a lot of work with deletion on PA4, so I'm not going to go through that in a lot of detail right now. But if you're not sure about PA4, right, go back and look at the delete code for that. And you know, the algorithm is basically replace the root with the largest thing in the left subtree. Or the right subtree, right? If you're not doing this for PA4, you can use either of those. Largest from the left or smallest from the right. In other words, the thing immediately before or after the root can take the root's place. And you know, if we want to keep our tree balanced, we might alternate those. We might do, you know, first deletion we replace from the left, second deletion we replace from the right, so that we're not constantly moving things out of the left subtree. But you know, either is fine. So I will not ask you about AVL trees. I will probably ask you about tries, though. So tries, remember our basic setup. See if I still have my try worksheet around. Hey, I do. So there's a kind of classic picture of a try. So your nodes are really wide, and you generally have one node, one pointer for each, in this case, letter of the alphabet, if we're storing words. So my node would have 26 pointers and then an end of word flag. And instead of moving left or right based on whether something is smaller or larger than the root, we move down one of these pointers based on what the first letter of the word is that we're storing. And once that gets us to a node, we follow a pointer based on what the second letter of the word is, and so on. So I might ask conceptual questions about tries. I might ask you to look at a try like this and answer some questions about what's stored in there. I might ask you to make some changes to a try like this. I'm not sure. Yeah, or an essay question, or write a poem about tries, or draw a picture. No, we did not code them, so I probably won't ask you coding questions, although I potentially could. I mean, I could give you a structure for a node like this and ask you to do something with it. But, you know, I am hoping that I will test you on things that, you know, we've talked about, worked with, or that you understand at this point. So, you know, hopefully I'm not going to give you any horrible surprises. But yeah, good source for conceptual questions. Dynamic programming, so, you know, that's PA5, that's this whole idea of caching. So, and again, the cleanest way to do this is just add something to the beginning and end of the function you're trying to speed up. So in the beginning, see if you've saved a value. If you have, return it. If not, do your regular function, and at the end, before you return, save the value that you're returning. And then everything else in your function stays the same. So it's really just an add-on at the top and the bottom. Let's see. All right, sorting. So what did we talk about with sorting? So you know bubble sort, insertion and selection sort. All right. So insertion sort, we do our work when we add our number to the output list. So you've got a series of things you're trying to sort. And for an insertion sort, you start with the first one and you put that in your output. And then you take your second one and you move that to your output. And you take your third one and you move that to your output. And you're always keeping your output sorted. And so the sort happens when you insert. Yeah, haikus would be awesome. Be a great exam. Tries are very cool. They have really big pointers. So much memory. There you go. There's my try haiku. All right. So insertion sort, we sort when you insert. Selection sort, you sort when you make your selection of what to move to your output. So I might go through here and say, oh, this is my smallest, so I'll copy that first. And then I'll go through and pick this and say that's going to go into my second spot. And then I'll find my third largest, which is here, right? And they're both order n, basically, to find, you know, which element you want to move to your output or where to put your element in the output. So those are n squared sorts overall. And bubble sort is also n squared. So those are the sort of quick and well, quick to code and slower to run sorts. And then we get into the log n or the n log n sorts. So merge sort is the one where you break your data into two sublists, you sort those, and then you interleave them so that the result is sorted. And that's a nice recursive sort algorithm, because how do you sort the sublists? You use merge sort, right? So you really only code up the interleaving part, and you just keep calling merge sort on sublist until you're calling merge sort on a single item, and then you don't have to do any work, you just return it. Heap sort deals with heaps. Obviously, we'll talk about heaps in a minute. Quick sort is this thing with a pivot. So you've got your data, and you've got one piece of one item. Usually we do the last one, that's the pivot. And we start moving in here, and we look for things that are smaller than the pivot. And when we find a spot where this is larger than the pivot, we stop. And then we come over here, and we're looking for things that are bigger than the pivot. And when we find something that's smaller, we stop. And so this is too big, this is too small, so we swap these two. And then we continue until we find something too big, and we continue until we find something too small, and we swap those. And once our two ends meet in the middle, that's where this should go. And when you've done that, then everything to the left is smaller, everything to the right is bigger. And so then all you have to do is sort this piece and sort that piece, and we do those with quick sort calls. So I posted some problems to work on a while ago on Canvas. I don't know if people worked on those or not, but just kind of, you know, going through step by step and trying to do this. So get some practice with that. Can we transpose a try? Transpose how? I don't know if pivot's related to 215 or not. Could be. Oh, transpose through linear algebra. I don't know if that would work, because it's not quite like a matrix. It's more like a tree structure, actually. just a really wide n-way tree. All right, so heaps, which was kind of the last sort topic we talked about. I think it was the last like new topic we really talked about. So heaps, max heap or min heap. So if we want to do a min heap, the fundamental property is that each node has to be smaller than both of its children. Right, so that's a totally fine min heap. And it's completely different from a BST, right? There's no notion of being, smaller on the left, larger on the right. The only notion is each node is smaller in this case than both of its children. And so that's a min heap. And because of that property, the smallest thing in the entire collection is always at the root. And so what are the basic operations? Well, you want to remove something from the heap. You want to add something to the heap. So removing, we always remove the root, and then we replace it with the last thing in the heap, because heaps always have to be filled in completely everywhere except the lowest level, and the lowest level has to be filled from left to right, so the heap shape, right? So we take the last thing in the heap, put it up to the root, and then we down heap, which means move down and make sure the heap property is satisfied. When you want to insert something, you insert it into the next spot to preserve the heap shape, and then you upheap. So you move up and you make sure each node satisfies the heap property, and if it doesn't, you swap with, in this case, the largest child, smallest child, and you keep going until the heap property is satisfied. And then heapifying a set of numbers. So we talked about an algorithm for starting with a set of numbers and building a heap without having to add them one by one to the heap. So there's problems on that I posted before too. And then the last thing was implementing this with an array. And if you store these in consecutive locations in an array, stored in that order, and you start with index 1 instead of 0, then there's some really simple index arithmetic you can do to find children, to find parents, and so on, and to find the first and last things. So we talked about this yesterday, I think, basically things you should be prepared to do. This is the same as on the midterm, right? So, definitely writing code, analyzing code, including recursive code, and, you might get conceptual questions on things that you do to these data structures, questions about makefiles, GDB, and so on. And I might have you do some sorts or manipulate some heaps or some hashes and so on. So that's pretty much it. We are out of time. That's all we got for this quarter. So I will see you for your final Monday morning at 10. Hop into Zoom so that I can mention corrections and errors and things like that. But there'll be an item on Canvas called Final Exam that will be locked until 10 o'clock Monday morning. That'll open. Download that. Type up your answers, submit those. Thank you everybody for the class. This has been, a really great class for me to teach. A lot of good energy. Even though it's online, it's just been a lot of fun for me. There's been a lot of energy coming from the students, and I really appreciate everyone's dedication to working on this stuff. So have a great weekend. Have a great rest of the week. I'll see you in 2:15 if you're there. Otherwise, I will see you Monday. All right, thanks.